All right, cool. And okay, here we are. So last time we started on this old decibel, and we went on, talked all about power, measuring decibel in terms of pressure. And I'll just kind of share screen here and get to that one particular PowerPoint that I want to show. And okay, now I think this is one of the slides here that we wanted to highlight. And it shows those two weird thermometers. And it just shows you that the softest you can hear versus the loudest you can tolerate. We'll call the softest you can hear kind of like freezing, and we'll call the loudest you can tolerate like boiling. And you see two thermometers here, and you can see where water boils if you see my cursor, and you can see where water freezes. And we talked last week, I introduced to you a whole pile of things about power first. And we said, what is the softest power that a person can just barely hear? And it's always this one condition. What's the softest that someone can, what's the softest for a 1000 hertz tone at 1 meter distance from a speaker with both of your ears? That is what we call the ground. That's going to be 0. And you can call that 0 dB IL, intensity level, which is power. Or you can call that 0 dB SPL, pressure. So dB IL, power, dB SPL, pressure. And either way, you can measure sound intensity in either method that way. Doesn't matter. Power kind of looks like what's produced, though, whereas pressure looks like what's received. And the ear is a receiving device, really, because it receives sound. So we'll choose pressure for that reason. We'll choose pressure for a second reason as well. Pressure, what's the softest pressure it takes to just barely hear a 1000 hertz tone at 1 meter distance with 2 ears? Well, we'll call that softest pressure 0.0002 dynes per centimeter squared. And look at the left thermometer here, right there, where I'm highlighting it, okay? We're going to call that our freezing point, our softest pressure. And the loudest pressure we can tolerate is 200 dynes per centimeter squared. And that's at where my cursor is pointing here. Now, the distance from the floor to the ceiling, if you will, isn't any bigger or smaller when you're talking pressure than when you're talking power. Let's go to the right. When you're talking power, boiling is boiling is boiling. Freezing is freezing is freezing. The decibel distance hasn't increased here. What's different about power is that the units are smaller. Look at these little tiny degrees. And I guess that's, so the softest power you can hear is 10 to the minus 16 watts per centimeter squared. And the loudest power you can tolerate is 10 to the minus 4. Well, the difference between the top and the bottom is 1 trillion to 1. It's 1 trillion increments. That means there's 1 trillion little, whereas if you go in pressure, there's 1 million increments. So the degrees are like they're a little bit bigger with pressure. But who cares? I'd rather deal with 1 million differences than 1 trillion differences. So 2 reasons we use pressure instead of power. 1, the ear is a receiving device. 2, there's only 1 million, only 1 million increments between the softest pressure you can just barely hear and the loudest pressure you can tolerate. Okay? And that kind of summarizes where what we talked a lot about last week. And I will stress that it's very, very important to always make sure that you stick to these notes and really make sure these Zoom sessions are the center of your academic learning in this course, because really that's where the nuts and bolts of it all is. Okay? Another slide that we talked about last week was this slide. And let's stick to pressure here. This is pressure. And you can see pressure units on the horizontal, dynes per centimeter squared. And the softest 0.0002. We'll call that freezing. We'll call that 0. That's 0 dB SPL, 0 decibel sound pressure level. And you can see that right here on the corner. Right on the corner and right on the prize. Anyhow, I used to live in Oklahoma City, and they had this advertisement by Oklahoma Discount Furniture. Oh, and right on the corner and right on the prize. Anyway, if I increase the pressure by a factor of 10, I've gone to 0.002 dynes per centimeter squared. And I've gone up by 20 decibels. And if I increase the pressure by another times 10, I've gone up 40, and so on. So when I keep going times 10, times 10, times 10, times 10, and so on, I'll get to 200 dynes per centimeter squared, which is 120 decibels. And that's why on the audiogram of human hearing, too, we run it from 0 to 120, you know, essentially. That's our decibel distance between the softest we can hear and the loudest we can tolerate. Okay, so there you go. But realize that 200 dynes per centimeter squared has 1,000,000 times the pressure of 0.0002. And by the same token, 120 decibels, look at the vertical axis here, 120 has 1,000,000 times the pressure of 0. And you know, the whole reason why we use this logarithmic weird times 10 times 10 system, the reason we do that is because we have to. The decibel distance between the softest and the loudest we can tolerate is that's so huge that we need a way to shrink it down. And what we've done is we've taken 1,000,000 increments and we've shrunk them down to 120. We didn't really shrink it. We just, our numerical units are fewer, because now we're talking from 0 to 120 degrees. You know what I'm saying? Instead of going from 0 all the way up to 1,000,000, we're talking 0 to 120. But we've done that because we used logarithms on base 10. We did this out of your text, 10 times 10, and then 10 times 10 times 10, etc. So without beating a dead horse, essentially, this is where we got to last week. And now we'll continue and finish off this unit on the decibel. And we'll go and look at the bottom of page 2. I think I'll flip over to the top of page 3. And where I'm reading here, and I'll let you see this as well. Here we are, and I'll scroll down. We covered all of page 1. We covered page 2 last week. I told you the middle of page 2 is for nerds only. Don't freak about it. Summary description of that decibel table. Well, you know what that is now. Basically, top of page 3, let's get out of power and stay with dB SPL. And to summarize the formula for dB SPL. dB SPL, where I'm grayed out there, is 20, that's the one thing, times the logarithm, that's the second thing, of a ratio. Okay, note the 3 parts, 20, logarithm, ratio. And to calculate any ratio, read with me what it says. You have to know what the bottom is. To say an apartment building is 2 times as tall as a house, we've got to define what's the ground. Well, we do so in sound with 0. But please don't think 0 dB means no sound. It means the softest pressure it took for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance with both ears. Okay, so that's what we defined it. And someone just decided to do that around World War II in the 1940s. That's when that came up. So here you go. The reference, where I'm grayed out there, the reference or ground for dB SPL, 0 dB SPL is 0.0002 dynes per centimeter squared. That's the ground. And so the bottom of the fraction will always be 0.0002. That's constant. Your denominator of your fraction is always going to be. And each time you increase the SPL by a factor of 10, you go up by 20 dB. So for example, what's the dB SPL for 20 dynes per centimeter squared? I just give you an example here. dB SPL is 20 times the logarithm of 20 over 0.002. You'll see it right there. And divide 20 by 0.0002, you'll get 100,000. What's the logarithm of 100,000? How many times does 10, look at my fingers, how many times does 10 have to be multiplied by 10 to get to 100,000? Well, it's got to be multiplied 5 times. 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, times 10 is 100,000. All right, so the logarithm of 100,000 is 5. 20 times 5 is 100. So what's the dB SPL that corresponds to 20 dynes per centimeter squared? 100 dB SPL. Only this time we didn't do it by looking at a picture. We did it by figuring it out with arithmetic. And so we'll move along down the page here, looking at pressure ratios, logarithms, blah, blah, blah. And you can see 1 to 1, 10 to 1, 100 to 1, and I just laid it out here. And so this table is merely this particular graph. That's all it is. Okay, now we get to some interesting stuff for today. Okay, we're leaving all that crap behind us now. Look where I've highlighted here. Doubling the sound pressure levels does not double the decibels because you're working with these weird logarithms. For example, and read with me, if you double the SPL represented by 20 dB, you don't get 40. You actually get 26. And that's only if the sounds are equal in frequency and equal in phase. So if two sounds are identical, read with me, if they're identical in frequency and phase, adding them together, you go up by 6 dB. I'll give you an example. Let's say you have a 1,000 hertz tone and it's 40 dB. 40 dB SPL. Always write SPL, never just say dB, okay? You'd say you have a 1,000 hertz tone and it's 40 dB SPL. Now you take a second 1,000 hertz tone and it's 40 dB SPL as well. What happens when you put those two tones together? When you add them together, 40 and 40 is going to total 46 dB SPL. You only went up by 6. Okay, this is just, it's just the way it is. It's with because you're working with logarithms. Okay, so for again a 1,000 hertz tone of 40 dB SPL, combine that with another 1,000 hertz tone of 40 dB SPL. 40 plus 40 is 46. Well, let's smoke another one. All right, take another tone of 1,000 hertz, and it's 40 dB SPL. And now add a second tone, but this one is not 1,000 hertz. It's a different frequency. It's 1,500 hertz, and it's 40 dB SPL. Okay, so two tones, both of them 40 dB SPL, and they're different in frequency. They're both 40, but they're different in frequency now. Now, 40 and 40 ain't 46 anymore. Now it's only 43. 43. Normally, and so this is what you really, this has bearing in reality, okay? Let's say you're at a factory and the machine in one corner is making 85 dB SPL, which is kind of loud. And let's say there's a second machine in the same room and it's making 85 dB SPL. What's the combined total of those machines? Both of them making 85 dB. Well, one thing you should assume is they're not identical. They're going to be a little bit different. Maybe one's going ring, ding, 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 and the other one's going ding, dong, ding, dong, ding, dong. They're making slightly different sounds. Well, guess what? They're not identical. Therefore, 85 and 85 You don't go up by 6 now. You only go up by 3. 2 machines in the same room, tally them together. What do you got? 88. Doo-dee-dee-doo. All right, weird stuff. Okay, here's what happens. Look at a pressure ratio providing everything, examples of the way dB/SPL works with ratios for sounds that are identical in frequency and phase. Okay, 2 to 1, you go up by 6. If you had 3 of them, you go up by 10. If you had 4 tones of the same everything, how much did you go up by? 12. If you had 10 of them, how much did you go up by? 20. Well, that makes sense. Look at the picture here. Increase by a factor of 10, you go up by 20. Makes sense, okay? And 20 to 1, and 30 to 1, and 100 to 1. How much did you go up by 100? If you had 100 tones, and they were all 1,000 hertz, let's say you have 1,000 hertz tones, you have 100 of them, and they're all 40 dB/SPL, each of them. You have 100 of those tones. How much did you go up by? Well, what does it say here in gray? 40. What's 100? Let's look at the graph. You go up by 100 from 0.002 to 0.02. You've gone up by 40. Okay, so back to our little example here. If you have 1,000 hertz tone and it's 40 dB/SPL, and you add 99 more of them, so now you've got 100 of those tones, each of 40 dB/SPL. What's your sum total? And you should be thinking, well, 100 to 1 is a 40 dB increase, so I guess I go up by 40. So if one tone was 40 dB/SPL, 100 of them, each at 40 dBs, totals 80 dB/SPL. 40 and 40 is 80. If you had 2 tones of 40 dB/SPL and they're 1,000 hertz, you go up to 46. You have 100 of them, your total is 80. A 2 to 1 increase is a 6 dB increase. A 10 to 1 increase is a 20 dB increase. So if you have 1,000 hertz tone and it's 40 dB/SPL, and you take 10 of those and you put them together. So let's say you have 1 and you add 9 more. So now you've got 10. You've got a 10 to 1 increase. How much did you go up by? 20 dB. So if one tone was 40 dB/SPL, 10 of those exact tones is going to total 60 dB/SPL, because 40 and 20 is 60. It's just simple. Just keep it in your heads, okay? But now, what happened? Look at here. In real life, you normally aren't adding things that are identical in frequency and phase. Think of a choir. You have one person singing, and then all of a sudden, the whole choir joins in, and now you have 100 people singing. Well, guess what? Each of those people is different. They're all different. So you can't quite use the same rule of doubling, you go up by 6, and increasing by 10, you go up by 20, and increasing by 100, you go up by 40. You can't quite do that. That's only when things are identical. What did we say about the 2 machines? When the 2 machines are different, you don't go up by 6 when you double the pressure. You only go up by 3. Just cut it in half. That's all you have to do. Okay? So if you have a guy singing, and he's singing at 60 dB, 60 dB/SPL, and then you have 10 guys, and they're singing at 60 dB/SPL, 10 of them, okay? Now remember, they're different. Because they're different, 10 of them doesn't increase by 20. Because they're different, 10 is only an increase of 10. Just like 3 is half of 6. When you double the pressure, if you tenfold the pressure, you only go up by 10 if the people are different, instead of going up by 20, as we would say on this graph. So this graph here is assuming everything is identical. Okay, if you increase the pressure by a factor of 10, if you have a tone of 1,000 hertz and you increase its pressure by a factor of 10, well, that tone is kept identical. So everything being identical, okay, you've just increased its pressure by 10, you've gone up tenfold, and that's a 20 dB increase. But in the situation of you have a 1,000 hertz tone, and then you add 10 more different frequencies, they may be all of the same intensity, but they're different in frequency. Well, now you're not going up by 20 anymore. Now you're going up by 10. Now I'm going to stop sharing the screen here. And what's a little different from last year is now I'm going to stop and ask, does this make any sense to you? Are you getting this? Does this make sense to you?
Unmute. I'm not quite clear on the half. I guess that's the easy way to figure it on the different frequencies, is just always know it's going to be half of what it was if they were the same.
That's correct. That's all you have to do. That's all you have to do. Let's pretend this way, Kelly. Pretend that Ted is singing at 60, oh God forbid, but he's singing at 60 dB SPL. Now pretend 99 clones of me, identical Teds. All of a sudden now, instead of one Ted singing, now there's 10 Teds singing. Oh my God forbid. Okay, how much do you go up by? If I'm singing at 60, okay, and suddenly now there's 10 Teds singing at 60, how much did I go up by? And that's a factor of 10, and everything being identical, I'd go up by 20, right? 60 and 20 will now total 80. So one Ted singing is 60 dB SPL, 10 Teds singing is going to be 80 dB SPL. Cool. Now let's think of a situation that's in real life. Ted's singing at 60 dB SPL, and then all of a sudden 10 people are singing at 60 dB SPL. Not 10 Teds, but just 9 more people. Like now there's 10 of us singing. Okay, instead of 60 plus 20 is 80, just 60 plus 10 is 70. Okay, and now let's draw that to real life. Good thing, because in a church choir, otherwise you'd be blasted out of the church. You think of some lady singing at 70 dB or whatever, and all of a sudden the whole choir joins her. My God, you'd be blasted out of the glass windows of the church would be blown out, because you'd have like 450 dB or something. That'd be insane. But the reality is, you don't go up by that much. You know, let's say if one person in a choir is singing at 70 dB SPL, suddenly the whole choir of 100 people joins in. Well, let's see, 100 would normally be an increase of 40 dB, but because they're all different people, 100-fold increase is only 20 dB. So now that lady was singing at 70, 70 plus 20 is 90. The sum total is 90 dB SPL. Cool. Got it? Good. All righty then. Great. Much better when I can actually ask somebody. It's way better. Okay. So basically, we've worked our way all the way down page 3. If you just follow page 3 down here, I'll do that with you. And look at this. You'd think I wrote this. So, one guy talking at 65 dB SPL, 10 identical guys would be a 20 decibel increase. See where I'm grayed out? But 10 different guys would be a 10 dB increase. There you go. Now, let's get to the fun part, and this makes it easier. Or this is just kind of, I don't know, just a different aspect. Read with me here in gray. In real life, you aren't always adding 2 equal decibels together. You're often adding 50 dB SPL plus 30 dB SPL, not 50 and 50. You're not doubling it or trebling it or making it 10 times the pressure or 100 times the pressure. Sometimes you're adding 2 different tones. They're not only different in frequency, they're also different in intensity. What happened? How now, brown cow? How do you add that together? Well, that is actually easier than you think. If you add 2 decibel levels where one is at least 9 dB more than the other, your total increase is closest to nothing. Look, bear with me. 90 plus 80 is essentially 90. And you know how you can think of that? Think of it this way. I'll stop sharing my screen and I'll just, an elephant plus a mouse is basically an elephant. Okay, if an elephant weighs a ton, if you put the mouse on top of the elephant, basically it's about a ton. It's going to be a little bit more, but who cares? I mean, the difference is so small, you really don't care. So that's why when you're talking logarithms here, 90 decibels is like the elephant. 80 decibels isn't just like, yeah, maybe 10 dB softer, but look what it actually represents in pressure. Because of logarithms, it's way less pressure. So 90 dB SPL plus 80 dB SPL is probably 90 point blah, 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 blah dB SPL. It's essentially bugger all. It's just like a flake. Okay? For another example, 45 here, 45 dB SPL plus 36. Well, they're 9 dB different. They're still 9 dB different. Basically is about 45. It's going to be 45 point something, but basically it's 45 for all practical purposes. And if you, here's a little table for guesstimating the sum of dB sound levels. If the difference between the two levels, read with me here, we're talking about the difference between the two levels and the amount of decibels that you'd add to that to the higher of the two levels, like 90 plus 80 is 90 essentially, right? So if that difference is going to be 9 or more, you add nothing to it. If it's less than 9, okay, now you got to start adding a couple of things to it. And I'll show you a little table that comes with that, just for fun. It's this. You look at this guy here. That's why you had this. And we won't beat the dead horse on this one either. We really won't. But here's an example. If you look at this particular picture, and at the bottom here, it says, let's say we're adding 85 and 90. Okay, we're adding 2 different tones, and they're different intensities. One's 90 and one's 85. Well, guess what? Those are not 9 dB apart anymore. They're less than 9 dB apart. They're only 5 dB apart. Okay? Now, to find the difference between the two numbers, it's 5. Find 5 on the curved line here. Look where my cursor is. The difference between 90 and 85 is 5. So 5 right here. Okay. Follow this point horizontally to the vertical axis. Okay. Note it intersects at about 1.2. See, this is 2 dB. This will be 1 dB. It intersects right there. Well, add 1.2 to the bigger of the two values. So it's going to be 91.2. 85 plus 90 dB, or I'll turn it around, 90 dB SPL plus 85 dB SPL is basically going to be about 91.2, basically. Okay, so, but it's just again, that's just a table. Okay, if the difference was, oh, look at this, if the difference was no dB, look at the top. If there is no difference, let's say if you're adding 90 and 80. Well, let's no 90 and yeah, let's say 90 and 90. There's no difference between the two. 0. See that? Well, how much did I go up by? 3. See, because they're different. Always assume they're different. 90 and 90, 93. Machine making 90 dB SPL, another machine making 90 dB SPL. Put together, how much did they go up by? 90. It's 93. 90 and 90 is 93. Oh, and one machine in a corner making 90, and the other one's identical, another identical machine, which is theoretically almost impossible, but two identical machines, 90 dB SPL plus 90 dB SPL is 96. Okay? Just little hiccups, little things there. Enough on that. Okay. A couple of things to always keep in mind about decibels. Again, this is just summary. Always remember that 0 dB SPL. I'll put an SPL right where my cursor is right here. Write a jam and it should read 0 dB SPL. Always remember that 0 dB SPL does not mean no sound. 0 dB SPL is just 0.0002 dynes per centimeter squared of pressure. And this is indeed something, even though it's tiny. And what's 0.0002? What does it represent? The softest pressure it took for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance with the two ears, sitting in front of a speaker. Okay? So you can actually have negative dB values. Look at this. You can have 0.00002. I got 4 zeros in front of the two here. See that? That's going to be minus 20 dB SPL. Don't blame me. It's just math. I just stuck another 0 behind the decimal. So always, always remember, 0 dB SPL is an arbitrary, deliberately chosen floor. We felt like it. We had to start somewhere, so we just arbitrarily made a decision one time. How are we going to define 0? Well, let's set some guy in front of a speaker about a yard away from a speaker. Turn on a 1,000 hertz tone. Measure the pressure at his eardrum. And find out the pressure that was required for the guy to just barely hear that tone. Okay, what pressure was that? 0.0002 dynes per centimeter squared. Okay, mark that puppy down. That's going to be 0. Okay, that's what they did. And if it was 10 times the pressure, 20 dB SPL. If it was 100 times that pressure, 40 dB SPL. 1,000 times that pressure, 60 dB SPL. 1,000,000 times that pressure, 120. By that time, the guy's going, ah, it hurts. Okay, got it. Now the good stuff. And I think Kelly's going to like this one because she's taking audiometry, 130. You can sometimes add decibels together, like 1 plus 2 is 3. You can sometimes, and we'll talk about how. Okay? You can't add 2 dB SPLs together like that. Remember, 90 and 90 is going to be 96 if the tones are identical, or 90 and 90 is going to be 93 if the two tones are different in frequency. Okay, that's because, how come? Because both of those are measured in dB SPL. When you add 2 dB SPLs together, you have to hold to that rule about 6 or 3 or 20 and 10. You have to hold to those rules. Okay? Because both of those values are referenced to the ground. The apartment building is referenced to the ground. The house is referenced to the ground. Any decibel value that is referenced to 0.0002 dynes per centimeter squared is a dB SPL value. And dB SPL values are called absolute values. They're absolute. It means they are both referenced to 0. Okay, remember the decibel is an arbitrary unit based on ratios. Remember the nominative way of assigning numbers to things? Ordinal is ranking, interval is ranking, but with equal distances between each item, and ratio had all those properties, but in addition, it called something 0. Okay, that's what we're talking about here. So when you have an 80 dB SPL sound and a 90 dB SPL sound, what's the sum total? Basically about 90. An elephant plus a mouse is an elephant. If you have an 80 dB SPL sound and another 80 dB SPL sound, you assume that they're going to be different, so the sum total is 83. If the 80 dB SPL sound and another identical 80 dB SPL sound are added together, 86. Okay, we're all good here. But when can you add 2 decibels like arithmetic? 1 plus 2 equals 3. There are some times you can do that, and that is here. If you are adding a relative dB value, if you're taking a relative value and you're adding that to an absolute value that is referenced to the ground, then you can add like 1 plus 2 is 3. And let me give you an example, because you're going to be doing this every day in hearing aids, because you're going to be hearing instrument specialists. Hearing aids. Read it again, right at the bottom here. Look at that sentence. Input plus gain equals output. Do you see that? Input is the sound coming into a hearing aid microphone. I'm going to stop sharing here so that we can really look face to face. This is very important. Input is the sound coming to the mic of my hearing aid. That's the input, and that's going to be some dB SPL. It might be a whisper, 50 dB SPL. It might be average speech, 65 dB SPL. It might be yelling. Who cares? Input is always dB SPL. Now, input plus gain. Gain is the muscle. Gain is what the hearing aid is adding. Okay? And gain is a relative dB value. Let's say the sound coming in is 50 dB SPL. And the hearing aid is adding 50 dB of gain to the input. Well then, guess what? 50 plus 50 is 100. Input plus gain is output. And what's output? That's the sound coming out of the hearing aid receiver. It's coming out of the hearing aid speaker, and it's hitting your eardrum. So input is the sound coming into the hearing aid. Gain is the lift, is what the hearing aid is adding to the input. And always remember, gain is a relative value, not an absolute. It's relative. Okay? I can't add 2 absolute values. I can't add 2 dB SPL values together like 1 plus 2 is 3, but I can take input dB SPL and add gain to that, just like 1 plus 2 is 3. Input plus gain is output. So input is dB SPL and output is dB SPL. What's not? Gain. Just the gain. And think of gain. What's the hearing aid gaining? What's it adding? What's it doing? And how come you know it's relative? Because look, I can add 50 dB of gain to a 10 dB SPL input. What's that? 50 and 10 is 60. It's going to be 50 dB SPL input, or I should say a 10 dB SPL input plus 50 dB of gain. What's my sum total output? 60. Okay, take a 20 dB SPL input. Add 50 dB of gain. What's my sum total output? 70 dB SPL. Take a 50 dB SPL input. 50 dB of gain. What's my sum total output? 100 dB SPL. Okay? Input plus gain is output, and the gain is relative. That 50 was the same for a 10 dB SPL input, was the same for a 20 dB SPL input, was the same for a 50 dB SPL input. It's relative. Okay? And thank God in our field, that's what we do. We fit hearing aids, and hearing aids add gain. And when you're dealing with hearing aids, we don't have to mess with one guy in a choir versus 100 guys in a choir and what's the sum total and dealing with logarithms. I just put you through that hell so that you could enjoy the dessert of input plus gain is output. But now you know what's behind the story. Now you can peel the veneer off the table and go, ugh, cover it again. Okay, because the decibel is based on logarithms. Now the people, let's see if I can grab this here for you. Shoot, I never have the stuff with me when I think I do. I'll get it for you. There we go. This is a sound level meter. People who walk around in factories, okay, they are the ones who have to think about logarithms. They are the ones measuring the intensity of machines in the corner. They are the ones who are going 85 and 85 is 83 and or 88, I should say, you know, or 90 and 90 is 93, and they're the ones using the logarithms all. They have to do that. Okay, you and I are dealing with hearing aids. And input, dBSPL input, plus gain, simple dB. Gain is always just dB. You don't have no SPL behind it. Gain is just dB. It's a relative decibel value. I can add 50 dB of gain to a 10 dB SPL input. I can add 50 dB of gain to a 50 dB SPL input. The gain is the gain is the gain, okay? Maybe my gain's 30, maybe my gain's 12, whatever. But for any input, that gain is going to be the same. It's relative. All right. Sound level meter people, stuff that we don't do. A hearing instrument specialist doesn't use these. These are used by people who are measuring occupational safety and health. They're the people who are following the laws of the state for noise-induced hearing loss, all that crap, okay? And we're going to touch on noise-induced hearing loss in this very topic this morning. So share screen again, back to where we were. We'll talk about simple decibel levels. This is important right here. These are things we should keep a grip on so that you and I as HISs can talk intelligently about what dBSPLs are out there. A whisper is about 45 to 55. All the other PowerPoints that I have on actual decibel values are a pack of lies. I put them in there because they're crap. Okay, they're junk. Don't listen to them. All right. A whisper is about 40 to 55. Which conversational speech 65 to 70. Memorize these. Okay. Yelling about 90 to 100, about 80 to 90. A lawnmower at close range, about 100. A jackhammer, about 120. Pain threshold, now it hurts, about 140 dBSPL. Always a whisper, soft speech, around 50-ish, okay? Average conversational speech, 60 to 70. Yelling around 80 to 90, okay? Oh, what's ambient room noise? Ambient room noise, when nobody's talking. So if I just sit here like this, what's the intensity of that? About 40 dB SPL, about 40. So you're never hearing sounds down to zero. We almost never do, unless you're in a sound-treated room where it's really quiet, and then you can hear your lunch digesting, okay, when it's really, really, really soft. Okay, but mostly ambient room noise is around 40 dB SPL. All right, inverse square law, don't freak, just kind of leave it. It just means as the distance from a sound increases, a finite amount of power is dissipated over a larger surface area. I think that was the slide that I showed you way up here near the beginning. I think that's this inverse square law. It says how much does sound get softer as you move away. Don't worry about it. I don't really care if you look at that or not. But you can read about it if you feel nerdy. It's okay. But sounds like, you know, slides like this are whoppingly inaccurate. I just don't believe so. Breathing, 10 dB? A dead quiet room, a very just ambient room noise when you're not talking is around 40. So I find this kind of a little bit misleading. I think it was meant for the general public. There's something else that's wrong with this slide. It doesn't have SPLs after. It's supposed to. Each of these would be referenced to the ground. Each of these would be an absolute decibel value. So just calling it dB, you'd think that's gain, and it's not. Okay, so it's inaccurate. That slide is stupid. This is talking about degrees of hearing loss. And people who are taking audiometry will already know that 25 to 40 dB of hearing loss is mild and moderate. But yeah, this slide is just, it's not going to be tested in this course because this course is not an audiometry course. But keep the slide for your own amusement. Okay, here we go. Another slide that's wrong. Okay, a whisper in a quiet library is more than 30. That's not, you know, this is again, it's kind of, I think these were meant for the lay public, and they're in the general, they tell the general story, but they're a bit inaccurate. I'd stick to the table that you had in my notes. This is a slide that's just meant to scare the hell out of you. Every time I look at this slide, I get kind of dizzy, so I move away from it. This is my favorite slide. I put this thing together, but that's because as a Canadian, I can deal with Fahrenheit, and I like to laugh at you who deal in Fahrenheit. Anyway, I'm just teasing you. This is out of your textbook. This is the graph we've talked about. Okay, here's another slide talking about what's out there intensive. A soft rustle of leaves, 10 dB? I don't think so. A whisper at 4 feet, 20 dB? I don't think so. See, these are wrong. It's just, again, I put them in there so you know it's just kind of, I don't know. And then, yeah, another thing, they don't have dBSPL again. It's just dB, which is silly. This is a slide. Okay, let's talk about noise-induced hearing loss. This is what we've got to get to. Very important that we move our way down the page here and finish this puppy. Yep, we're on page 4. So I'm going to go to page 4 in your notes. We'll move on down. Instrumentation that measures dBs. I think this is the very bottom half of page 3. Sound level meters. Okay, used for factory noise levels. I showed you a picture of that, or I showed you my sound level meter here just for fun. Look below. Audiometers are used to behaviorally test human hearing. Okay, human hearing. And audiometers test hearing at 6 or 7 octave frequencies. Remember, every time you double the frequency, you go up an octave. You test the decibel level required for the person to just barely hear the tone. This is important to remember. We covered this already. Total range of human hearing and frequency is 20 to 20,000 hertz. Audiometers test at the octave frequencies of 125 to 8,000 hertz. Each time you double the frequency, you go up an octave. Our very best hearing in this range tends to be for 1,000 to 4,000 hertz. Don't worry about that. Leave it alone. We'll talk about it after your midterm. So that's psychoacoustics. Anyway, allowable noise exposures before permanent noise-induced hearing loss. Most states, now this is important. This is where you are going to be counseling clients, okay? Most states allow 85 to 90 dB SPL exposure for up to 8 hours a day. As you increase the intensity by 5 dB, and sometimes the law is only 3 dB, well, then your time of exposure gets cut in half. So let's say 90 dB SPL is what the state law says. You can be exposed to 90 dB SPL in a factory for up to 8 hours. If the factory sound was 95, guess what? Your allowable time of exposure is cut in half. If the sound in your factory was 100 dB SPL, then you're only allowed exposure for 2 hours. Do you see the rule here? Every time you go up by 5 dB from your criteria, if your criteria is 85 or if your criteria is 90, whatever the state law says it is, okay, if you increase the intensity by 5 dB, your allowable time exposure is cut in half from 8. Think of 85 for 8 hours or 90 for 8 hours, depending on what your state law says. It's going to be either 85 or 90. And then as you go up by 5 dB, your time of allowed exposure is cut in half. Okay? Earplugs attenuate. Now that word attenuate means quieting. It means the opposite of turning up the volume. Earplugs attenuate. And this slide shows you by what? Earplug attenuation. Now, you ever see people who wear cotton balls in the ears? They just take cotton and they jam it in the ears. Okay? How much is that going to reduce the sound by? Well, look at the graph here. How much is it going to reduce 125 by? Just about nada. Okay? And only as the frequency increases past 1,000 hertz, now the cotton balls will start reducing the sound by about 10 dB. You see that? So jamming your ears with cotton doesn't really protect very much from noise-induced hearing loss. Then if you look at the bottom one, look at the, you ever see those yellow foam earplugs, yellow EAR plugs that people jam in the ears? Those are pretty good. If you squeeze them right, really squeeze those guys right, and then pull open your ear and you jam that way in your ear and you let that expand, those yellow foam earplugs, how much do they attenuate? Well, look what it says here. By about 30 dB in the lows and in the mids to 40 dB in the highs. So they really cut out sound. And when you are using earplugs, and Kelly, you're taking audiometry, so this might weigh home to you. But when you're wearing earplugs, you are giving yourself a conductive hearing loss on purpose. You're deliberately blocking sound, but your cochlea hearing, sound through the mastoid, is going to be perfectly normal. Bone conduction, normal. But because you're wearing an earplug, it's like you're artificially giving yourself otitis media, or you're artificially you're giving yourself a conductive hearing loss on purpose. And you want that because you want your threshold to go up to get worse. You want your threshold to get worse, but you also want your loudness discomfort level, your UCL, you want that to go up too. It's like an elevator box. You want the whole thing to go up. So earplugs are meant to give you an artificial conductive hearing loss, and you want that because you're trying to protect your ears. Now, look at the middle ones. These are called ER15 Musicians Earplugs. What's that? And notice how they block really flat. See how they do that? They don't have this drop or this drop like on the bottom. Musicians' earplugs are really quite cool. Now, if I can make my computer behave, because sometimes it does this. Sometimes it freezes up, and I don't know why it does that. So I'm going to stop sharing. I'm going to share screen again and see if I can unjam it, because I'd love to be able to go down one more slide. Oh, man. Yeah, sometimes PowerPoint freezes up like that. I don't know if you have the slide, but take a look if you have the slide and go further, and you're going to see a picture of a really weird earplug. My computer is jammed. I can't forward. Oh, there it is. Great, I managed to do it. Yay. These are Musicians' Earplugs. Now look at the bottom. Here's your foam earplug, yellow. And notice how it's got attenuation around 30, 35-ish, and then it's 40, 45-ish in the highs. Musicians' earplugs, especially the 15, it's meant to reduce the hearing by 15 dB all across the board. There's a reason for that. Now, unprotected ear, look at the top, the blue. Your open ear canal has a resonance, just like a wine glass. Remember we talked about quarter wave resonators a couple of weeks ago? I'm going to show you my coffee cup here. Here's that cylinder. It's open at one end, closed at the other end, just like my ear canal. Stop share, Ted. Look, here's my cup. This is going to be my ear canal. It's going to resonate, just like a wine glass at Christmas. Okay, and what is it going to resonate with? Because it's open at one end and closed at the other end, it's going to resonate with sound waves 4 times its length. Remember, it's a quarter wave resonator. Well, back to share screen here. Let's look at that picture. Your outer ear canal, look where my cursor is falling. It's going to resonate with around 3,000 to 4,000 hertz. It likes that. That's your natural, unaided, open ear canal resonance. And the high frequencies of speech are high frequencies, like 3,000 to 4,000 hertz. So your open ear was made to match the requirements for hearing speech, high-pitched consonants. Your ear is made for your larynx, okay? That's not an anatomy class. Back to acoustics, Ted. Here's your unaided open ear canal resonance. Musicians' earplugs are the red. They preserve that resonance. They just make it go down by 15. You see, if you take a foam earplug, a regular 50-cent earplug from the drugstore, and you squeeze that thing and you jam it in your ear, yeah, you'll protect your hearing all right, but the way it attenuates is going to look like it did earlier. And again, my PowerPoint is stuck here. I don't know why it does that, but you're going to get that uneven drop. Okay, here the drop provided with an ER. ER means etymotic research. ETYMOTIC. Etymotic research. It's a place out of Chicago. Okay, and they call it ER15. Why? Because it attenuates by 15 dB. And look at how it attenuates. It attenuates beautifully because it preserves the natural resonance of your unaided open ear canal. And by doing so, you can have your ears plugged with those things, but guess what? You can hear speech really well. Why? Because you're getting that same lift for the high frequency consonants. So musicians who want to protect their ears, but yet at the same time communicate with each other and not throw the baby out with the bathwater, musicians who want to protect their ears against noise-induced hearing loss, but still preserve the natural fidelity, the natural ear canal resonance, they will wear musicians' earplugs, which cost about $50 a piece. Okay, you get what you pay for. So they're very different. And again, my screen is just frozen here in PowerPoint. It just frozen. I don't know why it does that, but it does whenever I use Zoom. But anyway, so you're looking here, Earplugs Attenuate, not all the same. Musicians' earplugs versus regular foam earplugs. So this is essentially page 4. I think we're down at the very bottom. Yep, we're finished our talk on the decibel today. But it's very important that we look at what headphones do and what different ones do, because you definitely get what you pay for. I'm going to scroll up here and see. Oh yeah, that's good. We've covered everything that way. And that's the only thing that bugs. Oh, here's a pair of musicians' earplugs. Got it. Okay. Allowable noise exposure limits, whatever. Time exposure limits. This is a good chart. Here you go. This talks about noise-induced hearing loss. And here, in this particular state, hearing hazard doubles for every increase of 3 dB. So there's various wrinkles here. But let's say they call 85 dB. It's often when you see that A, we don't go into why that is, just leave it. 85 dB SPL, you might be allowed an time exposure for 8 hours a day. And then as the noise level increases by 3 dB, your time gets cut in half. By 3 dB, your time gets cut in half. By 3, time gets cut in half, and so on. Some states it's 5 dB, the time gets cut in half. Some states it's 3 dB increases, the time gets cut in half. Some states it's 85 is the beginning point. Some states start with 90. There's variations among the different states, but essentially it's going to be 85 or 90, and it's going to be as your noise increases by 3 or as your noise increases by 5. Either one, your allowable time exposure gets cut in half. And the time allowed starts at 8, and it goes down from there. The noise exposure level might be 85 or 90, but as you add either 3 or 5, your allowable time exposure goes down by half. That's the general rules of noise-induced hearing loss. Very, very common. Here's again talking about noise levels. Let's see if these guys are lying to us or not. A whisper, 30 dB, BS. A whisper is at least 40. Okay, so again, you got some inaccurate stuff here. Stick to the notes regarding typical sound levels. I would highly recommend this. It's the best way to go. I do believe we've covered just about everything that we got to cover. Next week, covering Unit 3. It's going to take 2 weeks to cover Unit 3. And Unit 3 is complex sounds. And what are we looking at there so much? Not pure tones and 1,000 hertz and if you double this. And we're looking at speech, the most important input to a hearing aid mic. Speech. What are the acoustics of speech? What is speech made out of? What's the frequency spectrum of speech? What's the waveform of speech? Because your clients at the other end of in your office are going to be wondering about hearing the speech of their loved ones. Hearing is about communication, and hearing loss is the one sense that not only involves the person who's got it, it affects the person's loved ones around him or her, because speech is a communicative sense. And so it behooves of us, when we learn acoustics, we better apply our knowledge of acoustics to the most important sounds our clients care about, and that's speech. So the most important input to a hearing aid is speech, and that speech might be a whisper, 40 to 50 dB SPL. It might be average conversational speech, 65 to 70. It might be yelling. It might be 80 to 90 dB SPL. Okay, keeping those numbers generally as our inputs, and always remember the dessert we get to have now, the cake. Input plus gain is output. Input is always dB SPL. Gain is always dB. It's just relative. And you can add that like 1 plus 2 is 3. Output is the sum total of input plus gain. And output is also dB SPL. So input and output are absolute values anchored to the ground called 0. Gain is just, well, did you add 30 to a 10 dB SPL input? Did you add 30 to a 20 dB SPL input? It's the wind. All right, we be done here. I'm going to shut up and get myself another cup of coffee. I need one. Kelly, you have a decent day. Lizzie, take care of yourself, and we'll see you next time when we look at you. That's a friend of mine would always say, I'll see you when I look at you. It's kind of like, yeah, I guess. All right, any questions? Does anybody have any questions? How are we doing? I should just stop here.
No, I think we're good. I just, the whole earplug thing kind of cracks me because I wear them at night because my husband snores.
Yeah, yeah.
But I still hear the snoring, and I guess it's because of I get that through the cochlea.
Well, and also the snoring might be louder than the earplug attenuates.
I don't hear the alarm clock half the time, and I don't hear if he speaks to me, but I can still hear. I don't hear it as loudly, but I do still hear the snoring. You
know why? They may not block the low frequencies as much as they block the higher frequencies. And the snoring is probably a low frequency and your alarm clock is a higher frequency.
Right.
Probably.
Right. That'd be my guess too.
Yeah. All right. Cheers. We'll see you next week, okay?
See you next
All
week.
Right.
Bye.